तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the technology of gallium arsenide very briefly, just an overview, okay, and we saw in this connection that it is required to have semi-insulating substrate, and on the top of that we need to have a epitaxy layer. In fact, if you have not seen it earlier, you can see the growth is gradually done layer by layer, and there are different techniques. What we saw yesterday or in the last lecture, one is a vapor phase epitaxy. We have seen there are at least 3 systems: halide, hydride and MOCVD. Okay. Though it is termed as chemical vapor deposition, real thing is vapor phase epitaxy, metal organic vapor phase epitaxy. I mentioned yesterday in the last lecture. Then we took a look at the molecular beam epitaxy to some extent. There are a few aspects which I still want to touch upon today. Then we will go on to the liquid phase epitaxy, which is not really very popular for microelectronics, but very useful when you want to have very pure layers for light emitting diode applications. We will see the reasons for that. So, first just go through quickly what we have been discussing. MBE is a process of depositing epitaxial films from molecular or atomic beams on a heated substrate under ultra high vacuum conditions. So, all that you need is a source which will actually supply those elements. So, these are the evaporation crucibles which are known as the Kunsen cells with shutters and heated substrate. The red, this color is the heated substrate mounted on a molybdenum substrate, which is chosen because of its high thermal conductivity, and the entire thing is enclosed in a stainless steel chamber, so that you can get vacuum levels of the order of 10 to the power of minus 10 to 10 to the power minus 11. I mentioned the reason, because if you have those high vacuums, you can get, you can see these are the, this is what is inside. What I am showing is only the source, the crucibles, the K cells, okay, for one for dopant, one for gallium, one for arsenic, aluminum, and for another dopant, and this is the shutter. These are shutters. You can see the beams are going like that, and this beam formation is possible because of very high vacuum of the order of 10 to the power minus 5 torr. If you have, you will have mean free path of about 10 meters, and if this distance is 30 centimeters or so of that order, it is quite good enough. But to keep the contamination level by a factor of 10 to the power minus 5, you must have vacuum of 10 to the power minus 5 further down by 10 to the power minus 5. That is you get, you need 10 to the power minus 5, 10 to the power minus torr. To give an idea, 760 torr is 1 atmosphere. So, way down below the atmospheric pressure, okay, virtually 0 pressure. That people talk of doing MBE in the outer space where there is vacuum. People talk of that, build laboratories there and do the MBE system there. You do not need all these things. So, you automatically have high vacuum there. That is what people talk of in the space labs. Now, the beams are thermally generated in the Kunsen type effusion cells which contain elements. That is, these are those cells which contain elements, gallium, arsenic, aluminum, all sorts of things which you want, plus dopants. Then the temperature of the K cells is controlled to an accuracy of plus or minus 0.1 degrees centigrade, because that controls the flux of the molecules or atoms. For example, you can see that you do not have to worry about this equation, just to show that the flux of these molecules, flux density, is related to the equilibrium pressure within the cell and also its temperature in this fashion, and of course, the angle between the beam and the substrate, normal to substrates. Okay, if it is theta is the angle between the beam and the normal. Okay, so if it is 90 degrees, nothing gets deposited, the flux is 0. If it is 0, flux is maximum. These are just some general ideas. Okay, you do not have to worry about too much about this equation, just projected also that the flux would depend upon the distance between the orifice and the substrate. More the distance, varies the square law, flux is slow. So, P is the pressure, temperature, mass of the diffusing species, Boltzmann constant, area of the orifice, that also controls the flux. More the area, naturally flux is more. Angle between the beam and the normal to substrate. Just to give some idea. Those who want to design the system, they will worry about that. The users may not worry about that much, because these are all fixed. The only thing that you have under control is the temperature and the partial pressure. Now, this high vacuum in the chamber is obtained by using pumps which are oil free. If it is a pump which depends upon some oil system, then there is a fear that oil may get into the chamber. In fact, in the conventional vacuum coating systems also, you have to be concerned about it. The best thing, of course, use some turbomolecular pumps which do not use oil. But in the conventional deposition systems, where you go for 10 to the power minus 5, 10 to the power minus 6 torr, okay, pressure, there are two pumping systems even in such a simple system. One is the rotary pump, which is pumped down to a millitorr pressure or so. Then the rotary pump is not able to pump down, because for pumping down, it is like, if you have a lot of water, if you put your hand like this, the water goes down. If there is vacuum, if you put like this, what will move? Nothing will move. That is why they use what are known as the diffusion pumps. Okay? You connect it to a system which is pumped down, and as you create lower pressure here, the molecules will diffuse from the chamber down to this pumping system. That is why, so those pumps are called diffusion pumps. Let me not get into more details of that. In fact, you will have a heater which will actually pump oil into the top, that will collect the molecules, bring down. So, to prevent the oil from entering into the chamber, you will have a liquid nitrogen trapped, so that the oil vapors do not go back into the system. So, that is why that blocks it. So, these are some of the things that you do in the conventional system, but here you may have more than one system, pumping system, to enable pumping of main chamber and auxiliary chambers and things like that. So, these are some of the names which you can just note that these are one or more of them are used in these systems. You can see there the diffusion pump also is there, okay, what I was mentioning, the usually pump. Growth rate in these systems is about 1 micron per hour. You can see that is very slow. You can control one atomic layer in 1 second, layer by layer in 1 second. So, in fact, you can get, because of that, very high quality layers with the MBE, molecular beam epitaxy. So, you can get thickness variation, or you can control the thickness within 1% over a 10 centimeter diameter or 5 centimeter radius for the entire wafer. You can do that. High purity materials can be grown, composition, thickness, doping can be controlled with high accuracy and uniformity. These are some of the advertisements for MBE system. In the sense, they are looked forward to because of these merits. This I just projected this to show you the difference between the simple circle that I drew for creating a chamber. The real thing is like this. If you want to have a look at this chamber or this MBE system, you can walk into our semiconductor research device research laboratory. There is one kept there which has been, is a very old system which is not really functional, but where there are some vacuum problems. So, what you can see here is the whole thing is a stainless steel chamber, into which you have got all these effusion cells 1, 2, 3, 4 is shown here, which are actually used as source of gallium, arsenic, etc., and also dopants. And you can see these shutters are also present here. Okay. When the shutter is kept closed, even though this is heated up, nothing comes out. When the shutter is opened, then only you let in the flux come out. So, depending upon what layer you want, you keep the shutter open. Undoped gallium arsenide you want, put gallium and arsenic shutter open. Okay. If you want aluminum or indium, you open the shutter which contains indium. Okay. The relative composition is controlled by this temperature, the flux. So, it becomes more involved here. Now, you can see this is the side which is giving those impurities, dopants or the constituents, and this is the substrate holder. Okay. That substrate holder can be rotated. We can rotate it, and this entire assembly is for rotating the substrate. Why do you rotate it? So that you get uniform layer, uniform thickness everywhere. You rotate it like that. So rotating the substrate holder, then some ionization gauges etc. for identifying what residual gases are present, things like that are there. More importantly, notice here there is one RHEED gun, reed gun. Okay, we will see it soon what it is. Okay, we will go back to that. So, this actually is high energy electrons which are gunned towards the surface at an angle of 2 degrees like that. So, it is slightly at an angle, and when it gets reflected there and that impinges on the fluorescent screen, you will see the pattern from which you can recognize the substrate quality of the layer. The reed pattern tells you about the thing. Okay, this is just an idea as to what all you can put there to characterize the growing layer. So, this is a very important component of the MBE system. And then you can also see there is a port in which you can view. So, that after all you must be able to see what is happening inside. There is a port there, okay, glass. And also when you see some of these things which are being inserted into the chamber, there is a chance for the leak in this portion. Even the minutest leak will bring your vacuum down from 10 to the power minus 10 to 10 to the power minus 4, minus 3, which becomes useless. So, they are actually not only this whole chamber is made up of steel, so that it does not degas, okay, and it is also between these two you will have actually those what is that the gasket, the gaskets which are there, because after all you can't bring two surfaces like this, prevent it vacuum tight. A slightly soft material which is gasket, they are actually made up of metal, gold, which I mentioned yesterday. So, those are the key things for getting this high vacuum, and also before turning on the system, the entire assembly will be put in a oven, a huge oven which is heated to degas the system. All that preparation of this chamber itself will be a big job. You must spend a week before you start growing the layer, okay? And once you start pumping down, you have to wait, the vacuum comes down to that level. And once the vacuum comes down, you do not want to open the vacuum to atmosphere, because if you open the vacuum to the atmosphere, you are back to square zero, because then you have to wait again. So, you can see that is why this small thing which is called as load lock, what is done is, that is the main chamber. There is a small mini chamber here, very small chamber. Okay. So, this gate will be closed when the run is made. So, you open this gate, insert the wafer into this portion through a whole wafer holder etc., keep it there, chamber is closed, pump this down. This is a small chamber, otherwise that whole thing is a big chamber. So, you have a small chamber here which can be pumped down rather easily, maybe to an hour. And when this vacuum comes down to acceptable level, if it 10 to the minus 10, you may have to go close to that here. Then open this gate, push the sample inside. Okay. And here also you do not push the sample straight away into the process chamber. There will be another chamber in between in the most modern systems, where it is a preparation chamber. So, one is for loading it, so that you do not open the chamber into atmosphere. Other one is the preparation chamber. The sample before it goes for epitaxy, you know that you should etch that substrate. So, you will have ion milling system just within that. So, you can see what all you can insert there for preparing the sample, for seeing the crystal growth, quality of the layer, everything will be done within the system itself. It is a huge one. I would urge that sometime you walk into our laboratory, ask one of us to show the MBE system that we have got, which is not running right now, okay, because of problem in vacuum. Okay, this is what I wanted to show you with the actual thing like this. Real thing you can see physically there. Major attraction for MBE is the use of this where we were yesterday, but I have added many more things to this previously now. Ultra high vacuum enables incorporation of high vacuum based surface analytical and diagnostic techniques like the read, etc. So, here comes the expansion for read, okay, RHEED, reflection high energy electron diffraction, okay, because after all these lattice atoms look like the diffraction patterns, okay, diffraction or gratings, and not diffraction, they look like gratings. So, when it falls onto that at 2 degrees 50 kiloelectron volt energy, high energy electron beams, they get reflected, they reflect the property of this, the atomic layer structure, because of the grating nature of the atoms. Okay, that is all what I can say about this. So, this is to examine the wafer just prior to and actually when the epitaxial growth is taking place. As I said, you can put number of things what you want for analytical examination. Mass spectrometer, you want to monitor what are the gases which are present there, are there any contaminants, all that is done in the chamber using the mass spectrometer. You can also have for surface analysis of the sample OJ electron spectroscopy. This is the electron and the particle, one more emitted particle, 3 particle phenomena. So, these are just some of the names which you will hear: OJ electron spectroscopy, X-ray photoelectron spectroscopy, secondary ion mass spectroscopy, all spectroscopies to see what sort of surface you have got as it grows. These are the benefits that you get when you use the MBE system. Because of that, you can get high quality layers, because you can ensure that the contaminants are not there, and you can ensure that the growing layer is perfect. In situ you can examine. You do not have to take it out and say, let me see what I have got. You see it right there. Now, the modern MBE systems are, as I told you already, are generally multi-chamber apparatus comprising the fast entry chamber, load lock system. Load lock means you load it then lock it, okay, and a preparation chamber where you prepare the sample to get it ready for deposition by cleaning the surface either by plasma etching or by ion milling, and then the growth chamber. That is the real one where you expose it to the constituent elements. This of course are the placed, okay, these systems AES, XPS, etc. are placed in the preparation chamber, so that contamination can be reduced. You can pull it out there itself you can test after the growth is done. One thing is during the growth using read, other one is after the growth and before the growth in the preparation chamber. Gallium arsenide with carrier concentration 10^13 to 10^14 undoped have been achieved. With all this care, you do not get 10^6. You are there 10^13. People are now able to go below 10^13 because you are able to have the sources which are purer. Gallium source 7 purity, and along with that, the mobility of the carriers in those samples has improved. Okay, we will come to that when we discuss high electron mobility transistors. Residual impurities. Now, what are these impurities which are present in this MBE system? They are, one of them of course, silicon omnipresent everywhere, carbon giving rise to p-type condition of that dopant. Carbon gives rise to p-type. Okay. Now, silicon also incorporation depends upon the temperature, it can be p-type or n-type. So, you get p-type there. Mostly you get p type when you do MBE at 600 degrees centigrade. Okay. That 10 to the power 13 doping. So, you will say it is undoped layer, but of the order of 10 to the power 13 carrier concentration, undoped p type. Where do these impurities come from? If say silicon, it comes from gallium. You are using the gallium source, that is coming silicon impurity is present to some extent. Carbon, whatever residual ambient is present in the UH ultra high vacuum, that contains carbon. Okay. In the atmosphere that is there, there will be a little bit of carbon. Then you have also manganese from the hot stainless steel chamber. Okay. These are the contaminants which come up. Now, disadvantages of MBE. All merits are there. Okay. Disadvantages, of course, is very clear. It is complex, and one will say it is costly. How costly it is depends upon how many gadgets you have added onto that. If you have just a vacuum chamber which can go to 10 to the power minus 11, that may not cost you much. You may end up spending something like 50 lakhs or maybe 1 crore at the most. But if you add all those gadgets, then it goes to 2 to 3 crores, 3 crores. Okay. So, that is the cost. When we bought way back in 1980 this MBE system, which is just a simple system, only the read system was there. Without read, RHED, there is no use. You do not know what is happening, whether you are getting good layer or not. That I think it was at that time about 25 lakhs. But 25 lakhs that time, you know, if equivalent rupee you see now, 25 lakhs of rupees, it is equivalent to 2 crores, because money value has that much come down. Now, this whatever we have been discussing is the MBE system with the source from these K cells. Now, there is a problem with the system. We avoid the problem of exposing it to ambient during loading by having the load lock system. Now, those K cells which are sources of gallium, arsenic, etc., somebody has to fill them up. You have to have say 10 grams, 20 grams, 50 grams if it is a huge one. That amount of element you must put there. How do you put that? Open surgery. Okay. You have to open it totally and then put that. And once you do that, you know, it is so many contaminants go into the chamber, and you have to pump it down. It is a lot of work. So, that is one of the problems. So, okay. So, that is what that is. MBE using elemental solid sources requires opening the high vacuum chamber on a regular basis for replenishing them. You want to fill them up. Now, if you use gaseous sources, you overcome that problem. Okay. Now, just what you do is, there are two types. When you say gas source, you can use only for arsine phosphine, that is arsenic and phosphorus if you want. Do not use elemental phosphorus, do not use elemental arsenic, use arsine and phosphine gas, and the gas source is outside the chamber. You have a flow meter, etc., mass flow controller, the gas will enter into the chamber instead of the K cell. There you can crack it by heating it up. Okay. So, when you use for fifth group alone arsine phosphine, they tried it first, that they called it as gas source MBE, GS MBE. But later you have got now MBE systems which are called as MOMBE, metal organic MBE, means it is a MBE system in which the elements are obtained both for third group and fifth group using gases. Gases or vapors. For example, organometallic alkalis for group 3 elements, and also gaseous hydrates such as arsine, phosphine, etc., for group 5 elements, when used Say for example, for gallium, trimethyl gallium, bubble gas through that, let into the chamber. For indium, trimethyl indium, aluminum, trimethyl aluminum. So, all those sources are all liquids. Let bubble gas through that, let it into the chamber. Okay. And for the fifth group, arsine and phosphine. So, such a system is called MOMB. So, it's some people think that you put the MOCVD inside the MBE system. I heard some people say that. It is not like that. You use metal organic sources outside. Okay. When you do that, now you can see the two systems, whatever I have put in words is seen here. This is the gas source MBE. Okay. And you can see here, this is gallium, this is indium, elemental, third group. And then the dopants like beryllium, silicon, etc. are also put here. They are within the chamber. Within the chamber, this will be given afterwards. And you can see only for arsine and phosphine, use it from outside the chamber. So, only for fifth group you use the gas, that is called gas source. More general term, that is the MOMBE. This is more closer to the system, what you see. So, that is the chamber that we are showing, and you can see there is one port through which you can let trimethyl aluminum, trimethyl gallium, trimethyl indium, and these are the valves you can close if you do not want those elements coming in, vapors. It is not element, it is a vapor, it has to be cracked inside the chamber, and all the shutters are there as it is. This is the heating part of it. Okay. So, organometallic compounds for third group all mixed together through one port, then phosphine, arsine all mixed together for one port. If you do not want arsine, close this, you close this here. If you do not want phosphine, close this here. So, you have got complete control from outside world, and when this is empty, you replace this bubbler here, you replace the gas cylinder here, you do not have to open the chamber, you never have to open the chamber. Okay. Everything done from outside. So, you pump down and start running it, and these systems should be on all the time, and that is why you need uninterrupted power supply for these systems, because once the power fails, its pressure comes back to atmospheric pressure. So, this is the MOMBE source. Okay. Now, here also you can see that reed system is there, and for monitoring the residual gas, that is mass spectrometer or whatever it is also there, substrate is shown here. Okay. This is the most modern version of MBE system called MOMBE. You can imagine the cost of that would really go up, much more complex, and you have got the complete benefit of MOCVD and also MBE. Merit of this MOMBE is the composition of gallium indium arsenide, for example, you can control, you have to vary X. Composition of aluminum gallium arsenide, you have to vary X here. This can be precisely controlled by pre-mixing the gases before entry into the chamber. Here, you can precisely control the flow of these aluminum, flow of gallium, gallium meaning actually the vapor, trimethyl gallium, CH3 thrice Ga. That is what is meant by that. One more advantage of this MOMBE system is, which is what I have called it as beam fading effects are absent when the shutters are opened. What is implied by this is, in the conventional system, okay, let me just go back to that to show you that. I will come back to this afterwards. In the conventional system, when you start, normally when you have the shutter closed, okay, the temperature is set by this, set to 1000 degrees. In fact, the temperature here could be 1000, even more than that within a K cell. So, that is hot. Okay. The vapor pressure, everything is decided by the temperature. the moment you open it, okay, there is a cooling effect. The chamber is not hot, there is a cooling effect. Because of the cooling effect, the beam intensity goes down. It enters into that K cell. So, beam intensity goes down, that is called the fading effect. Now, in the gas source system, the source is outside, you have the control, no fading effect. Even if that cools down, the flow is there. So, that is what we meant by saying in the MBE system, because this is outside the thing, you can control the flow of these constituent elements externally, the fading effect of the beam is not present. Okay? This is a general guideline to show you what are the vacuum levels which are used generally. You can see the MOCVD, hydride vapor phase epitaxy etc. are done at atmospheric pressure 760 torr. You can also have low pressure CVD, okay, where you get certain benefits which that will not go into, okay, all the, again when you go to low pressures you get the benefit of longer mean free path. So, when you put a wafer like this, you can put one wafer behind the other one, if the gas is flowing, if it is atmospheric pressure, the deposition, if you put the wafer vertically in the furnace like that, it will deposit on this, it will be blocked. If you go to lower pressure, the mean free path is long, so gas is flowing here, it can flow like that all through. Okay. So, you have hindrance effect is not there. Okay. And when you mount the wafer vertically, you have the benefit of any particle that is present will not stay on the wafer, it will fall down. That is the benefit of that. That is why people advocate for low pressure CVD system, just it is not very high, very low pressure, -3, -2 torr. Then you have got MOMB etc., where the gases are coming in, there the pressures are not that low during the deposition. Please remember, these are the pressures during the deposition. Before you start, you better pump down to 10 over -5 -11 to avoid any contaminants. And in the MBE, of course, there are elements which are getting heated up, very small quantities, that is 10 to the power -4 during deposition. Growth, chamber pressure initially will be -10 to -11. When you let in the molecules, the pressure automatically will go up. Okay, the last one in the epitaxy, last but not the least, so to say, is the liquid phase epitaxy. Liquid phase epitaxy, as I mentioned earlier, okay, involves growth of epitaxial layers on a single crystal substrate. All the epitaxy involves that, and this is by direct precipitation from the liquid phase. Okay. That means you keep the wafer or the substrate in contact with the liquid, and from the liquid you allow the freezing to take place. Very popular for gallium arsenide light emitting diodes etc., because epitaxy of compounds are grown from the melt at temperatures well below the melting point of the compound. That statement will be clear from this diagram. Okay? Look at this diagram. I hope you are able to recognize that. I have put one half of the phase diagram. See, here is gallium, the center 50% gallium, 50% arsenic, if you get gallium arsenide. On the other side, it will go like that, where arsenic is 100%, that I have not shown, because this is sufficient to illustrate the principle of liquid phase epitaxy. Usually, in the Czochralski technique, you are growing from the melt. It is a melt grown system. Okay? You are going from there. That is the melting point of stoichiometric gallium arsenide, 1238 degrees centigrade Tm melting point. Now, from there from the melt, when you pull the crystal, it is as good as you are coming down in temperature. Okay? As you pull it out, your liquid solidifies and you get gallium arsenide. This curve I have just expanded. Actually, this whole thing, that red thing, is one line there, as I told last time. So, this is stoichiometric gallium arsenide or slightly off stoichiometric. So, this transformation from here straight to the solid without a liquid phase, from liquid to solid straight, that is called congruent transformation. You get directly gallium arsenide. So, in the Czochralski process, you use that from the melting point 1238 of the stoichiometric compound you are using. This is necessary because that is quite fast. You can grow at least in a day reasonable length of crystal. Whereas, in the liquid phase epitaxy, I think I mentioned it earlier, but this is a clearer diagram. You can see this is gallium melting point 29.5 degrees, gallium arsenide melting point. You go down somewhere here. Okay, you have a liquid. See, above this line it is liquid. If you move this side, it is gallium rich. If you here, it is totally gallium melting point is 29.5 degrees. So, somewhere 600 or 700 degrees centigrade if you grow, have the liquid of this composition, that is gallium which is saturated with arsenic. If you have, when you come down to this particular temperature, it will have that composition. Okay. Even if you have liquid lot of arsenic, when you come down in the temperature to this particular point with a particular gallium, that will be the composition C naught. So, let us say you start with, keep the substrate in contact with the liquid, okay, which has the composition C naught. Okay. C naught amount of gallium, or the ratio gallium to gallium arsenide to gallium or arsenic to gallium, some composition is there. Now, you start freezing from that liquid. When you freeze here, this portion here completely below this liquid line and up to this is the solid line below that, this portion has got liquid and solid both. In the sense, here the difference is you get straight away solid. That is the congruent transformation property of this phase diagram. Whereas here, when you start freezing, you get precipitation of solid, and that precipitating solid has a composition given by that. That is the property of the phase diagram. Okay. You must understand, and from here you freeze, if you see where the solid is, that is the composition. That means, when you freeze from a temperature like 600 or 700 degrees centigrade, the freezing compound or freezing solid is nothing but gallium arsenide with composition that one. That is close to stoichiometric. Whether it is gallium rich or arsenic rich depends upon actually from which point you are freezing. Okay. But what you get is gallium arsenide which is close to stoichiometric temperature, stoichiometric composition, growing from a very low temperature. Of course, I should caution those who are in the physics, say low temperature. It is not low temperature, it is lower temperature compared to melting point. Okay. You get gallium arsenide. This is the benefit. The major benefit of growing gallium arsenide from a melt, this is called solution growth. From a solution, you get gallium arsenide much lower temperature than melting point. What could be the benefit of this? Okay, now when you do that, slightly when you come down, you get that composition, it loses that gallium. So, the gallium concentration comes down. So, when you slightly come down along this curve, what happens is, when you freeze, I am just showing it slightly below, but for clarity I will show it a bit below. The freezing compound will have that composition, and the liquid composition will be on this side. So, you see where is the solid, where is the liquid. You project onto the liquid curve, liquidous curve, that will give liquid composition. Naturally, when you freeze, you lose gallium, so the gallium richness comes down. Okay, you lose, the composition changes. So, what you see is from here, what we are worried is not what happens to that, what happens here, that is the freezing solid. Okay, now let us see what is the merit of this. What is the merit of freezing and getting gallium arsenide at a lower temperature. Contaminants are less. Why do you say contaminants are less? What contaminants do you worry? You worry more and more about the deep levels. Deep levels you do not want in this system now. Okay, you are going, let us say, N type gallium arsenide. You want to make a PN junction for a light emitting diode. When you want to make a PN junction for light emitting diode, what do you want? Let us just see. You need actually EC and EV. If I take, you want for the light emitting diode, for the particular material, the electron from here must make a transition from down here. During that time, it will give you the light corresponding to that band gap, 1.24 divided by the band gap, so many microns, that is what you get. Now, if there are deep levels, deep impurities like heavy metals, copper and things like that, that can be present in the liquid. If they are present, the transition is from here to here and here. Many other electrons may go through that transition. Now, what is light emitted by this? Correspond to that wavelength. So, it is entirely different wavelength. If you are looking for red light, you will not get red, you will not get anything, because the energy is very small. So, energy is very small, which will be very long wavelength, you will not even see. If you have light emitting diode, you will have dark, okay. You will not have any light, but there will be some electrons which will be making transition like this. So, some of them will make transition like this, many of them will make transition like this. What is the impact of that? The impact is the quantum efficiency, the efficiency with which light is emitted goes down. So, you want very pure material. Now, with the liquid phase epitaxy, what happens is, this is a very important thing that to note down, these levels are absent. All those deep impurities do not go into the solid when the temperature is low. Okay. Here a metallurgical term is used, segregation coefficient. If you add into a melt some of the deep impurity like chrome, gold, copper, etc., if they are present, and if you solidify that, the segregation coefficient means if there are 100 copper atoms, how many go into solid? It may be 0.1, 0.01. How many go into the solid depend upon the temperature. If you are able to freeze at lower temperature, like this here, the number of those impurities getting into solid are less. Segregation coefficient is low at lower temperatures. So, when you solidify at a lower temperature, get this gallium arsenide. That gallium arsenide has very few impurities, and that is not present, you get excellent light emitting diodes. So, this is the key for the success of light emitting diodes, and this is the one that is used. In fact, a very simple system, you do not have to spend crores. Okay, you do not have to spend crores for this. I put that down. There is a principle where you freeze it and actual system like that. Very simple. All that you need is to get in touch with a company which makes some graphite blocks. I am not getting money for advertising. The Poco graphite, that is very famous graphite making company, very high purity graphite they make. So, the whole thing is graphite block. You have got a big graphite block in which another graphite can slide. This is the sliding graphite, the middle one, okay. And this block, this entire thing has a hole which can slide that graphite. There is a bin, a hole from the top. This is a cross section. What I am showing is a cross section. So, in the top you have a hole, okay, and here up to certain depth that hole is there. So, when this slide goes inside there, that hole is covered there. So, what you do is you fill in the solution. Okay. In fact, gallium and with very arsenic rich gallium arsenide. If you want to grow gallium arsenide, you put the solution there in this, and this is a graphite cover. Whole thing is graphite, because it does not affect the gallium arsenide solution there. Now, this is actually a substrate. That could be the semi-insulating substrate which you have put. So, on that slider you have a depression where you can put the wafer. So, okay, you get the idea. So, this is a depression in which you put the wafer. I am showing small one, but maybe 1 inch, 2 inch or 3 inch. Put it there, heat this up to the required temperature. Just let me see whether I have that there. The entire system is placed in hydrogen gas ambient, okay, and the temperature is raised to T1. How do you do that? This is the graphite block with the facility to push and pull the slide, and a facility to keep the wafer, and a facility to fill this bin with the liquid. Okay. Now, this whole thing you keep it ready, put it in a furnace. Furnace does not cost much, maybe 5 to 10 lakhs, okay, and this will not cost much. So, you have got the epitaxial system with at your disposal with 0.1 crore, okay, 10 lakhs of rupees, 100,000 rupees. I am sorry, 100,000 is 1 lakh, 10 into 10. Okay. So, here what you do is, let us go through that. So, that system is kept in the furnace, raise the temperature to that point where you want, say 700 degree centigrade, temperature raised to T1. T1 is that temperature where you want to grow. Now, substrate is brought under the bin, and the furnace temperature brought down with temperature gradient ranging from 1 degree centigrade per minute or 1 degree centigrade per 1 hour. Can you imagine that? I want to drop the temperature, program such that the temperature falls from 700 degree centigrade to 699 in 1 hour. So, it is very small change. Why? That is why, because you want to remain at that level, at the same time you want that the gallium arsenide to freeze onto the surface. So, what you do is this, the statements that are made there in that thing here, substrate is brought under the bin, means the substrate is, that is this graphite slider is pulled, so that this is coming in contact with the liquid. Now, all that you are doing is, you are ultimately what you achieve is, you have that where the liquid solution gallium arsenide is there, and it is as good as placing this substrate below that. So, slightly reduce the temperature, then you have got the solid particles which actually ultimately come, and you get the epitaxy. Okay. So, it is a very slow process. Okay. That is why you can't use it for making the gallium arsenide wafers. You can use it for making very thin layer of N type or P type, because you can add impurities into this if you like, or you can change the temperature and get P type and N type, that we have mentioned earlier. So, that is why the entire control here is ability to grow liquid phase epitaxy is control on the temperature, programming in the temperature. Then after once you have grown, let us say half a micron, 1 micron, after an hour or two, what you do is you pull that slide out. That it was sitting here, you pull that out. Now, this terminates the entire growth process, 1. Number 2, when this was in this position here, the liquid is on the top. When you are pulling it out like this, you are wiping out whatever fluid is left out, double purpose. Terminate the reaction, wipe out the surface, so that whatever liquid is there is gone. So, you do not need further cleaning on that. You get the epitaxial layer on whatever substrate you have got. You can have compositions varied by varying the composition of this fluid. That is what is done in liquid phase epitaxy. Okay. Advantages, of course, are, I think I am almost towards the end. The advantages of the epitaxy of compound semiconductors is done at lower temperatures. As I mentioned, segregation coefficient is low, so deep level contamination is low, excellent for LED, light emitting diode applications, to achieve better quantum efficiency. Now, if you are fancying, I can make layers, gallium arsenide layers suitable for microelectronics applications with 10 lakhs of money. There is one problem. The problem is that layer that you grow, uniformity is not very good. The thickness uniformity is not very good, because it's after all, it's just freezing from the liquid. So, you do not get control over thickness uniformity of this wafer. So, if I have a big wafer like that, 4-inch diameter wafer, I am still talking of inch because people are used to that, 4-inch wafer diameter, and if I am growing, if it is varying all over the place, it will be all right for you are making LED, light emitting diode. Slight variation does not matter there, because it is after all what you need is a junction. Whatever happens is happening at the junction, PN junction. But if you have a layer like this, if I have a semi-insulating substrate, gallium arsenide, on the top of that you want to grow this layer. This is the epitaxial layer or epi layer. Okay? That is the epi layer. That must be uniform for microelectronics applications. In fact, you will see, if you want to make a field effect transistor in this layer, if it is n type, you want to make a field effect transistor, if it is not uniform thickness, entire your logic circuit functioning will not be good, because if you want to make digital or analog circuits, because threshold voltage of those FETs would depend upon the thickness. Okay, you may not agree with me right now, because if you see, take a look at the MOSFET threshold voltage will depend upon doping. But even if you make a JFET or MESFET, the threshold voltage will depend upon enhancement mode particular type, depend upon the thickness. And if the thickness is varying over the entire surface, what will happen? Threshold voltage will be varying, and you don't know what is happening, the malfunctioning of circuit. So, that is why they are not suitable for that. Okay. Now, few things I want to mention before I wind up this particular discussion. What we have said now so far is for gallium arsenide microelectronics or even for light emitting diodes, you would need epitaxy layers or you need an active layer, and epitaxy can be done to get the active layer either by MOCVD or by MBE or MOMBE. Choice is yours depending upon how good quality you want and how much money you have. Both are taken care of. There is another approach which is followed very popularly. All that you need is, you need to have an N-type layer. In fact, an excellent approach is, do not go to that epitaxy layer, use one equipment. The one equipment that you can use for realizing N-type, P-type, all sorts of things is ion implantation. I have no intention of going into details of ion implantation, but just to show you, you can actually take a semi-insulating substrate. Okay. Take a semi-insulating substrate like that, cross section, semi-insulating gallium arsenide. I do not need to put the implantation everywhere, the dopants. I put somewhere here. I can implant dopants. So, I can make that layer N-type. Once it is N-type, I can use that for realizing FETs, and this is semi-insulating. I can put Here also n type. You can see the interesting part of this is you have got n type here, n type here, isolated from each other. You can't ask for more than that, because when you want to make devices, you want them to be isolated. Basically, you want them to be connected when you say it must be connected. Okay? Otherwise, they must be isolated. The isolation is provided by means of this particular layer, semi-insulating material. So, ion implantation, if you have an equipment, you can use that for totally for realizing these structures. Okay? All that you would need would be ability to implant and realize this, and then make devices on this. What device would you make? So, either use this device, this implanted portion for making devices, or you can use the epitaxy layers for making devices. So, next question is devices using epi layer or implanted layer, okay, or implanted layer. That portion, that these topics we will discuss next time, okay, because that is where we now begin our discussion on devices. We are ready now with the material, semi-insulating substrate, epitaxy or implanted, then make device. What sort of devices we make? Whether it is MOSFET, is it feasible to make MOSFET? That aspect we will discuss first. If it is possible, you do that. Otherwise, go to MISFET, not MISFIT, MISFET. Okay? That is MIS, instead of using the native oxide, some other insulator. That sort of thing we will discuss in our next discussion. Okay?